Welcome to Abstract Synthesis, where we share the stories behind interesting academic papers in the world of program synthesis and neurosymbolic AI. This podcast is brought to you by AGI Research Lab and DIA, and I'll be your host, Brian Landers. Today, we are speaking with, I think, a total program synthesis badass. We'll see what he thinks of that characterization. He's an associate professor of computer science at the University of Wisconsin-Madison. His research group is focused on automatically synthesizing the software stack for future quantum computers. How cool is that? I can't wait to get into that. And he also is getting into the very timely work of AI agent construction and correctness. So maybe if there's time, we'll cover that. But I want to welcome you to the show. Can you please introduce yourself?
Yeah, thanks, Brian. My name is Aws Albarghouthi, and I've been a professor here at Wisconsin for over a decade. I'm in the computer science department, and I'm from the programming languages and formal methods community, broadly construed, and I study program synthesis primarily, and I've been applying it to all kinds of domains over the past decade. And more recently, as you said, it's been focused on the quantum computing stack and how can we automatically synthesize it as things are moving fast.
Okay, I'm tempted to dive in on quantum stuff right away, but you have a pretty, very well-cited paper called Recursive Program Synthesis that really jumped out to me because this show is about program synthesis. So it feels like we kind of have to cover that. It was co-authored with Sumit Gulwani, who's famous inventor of flash fill and leads the Microsoft Prose team, one of the members of which we've had on the podcast. So we're gonna dive into that a little bit, and then we'll get around to exploring the quantum side. But before we even get into the paper, I'd just love to learn a bit more about you and your work because it's so impressive in this space. How did you make your way into the world of program synthesis?
Yeah, so I went to graduate school to study formal methods. I was attracted to logic and being able to concisely and precisely describe the world with the language of logic. And that drew me to the world of software verification and constructing proofs. So in the late 2000s, early 2000s, there was a lot of action in automatically proving programs correct. And I started working in that space. How can we automatically construct proofs? And as you know, proofs are very much like programs. So that kind of eventually towards the end of my PhD as a side project, I started dabbling with program synthesis because by that point, the programming languages and formal methods community had rediscovered, let's say, program synthesis. Program synthesis had been, alive for a very long time, but had been somewhat dormant. And by then, people had started relooking at it, including Sumit at Microsoft and others as well. So we started dabbling on the side, and that drew me closer and closer to that. And when I started my career as a professor, I went all in, applying program synthesis to all sorts of areas, and I still do, and I have that program synthesis hat on pretty much all the time. Yeah.
I love that. Okay, you are our people. But backtrack for a second. You actually did some research work at Microsoft, right?
I did a bunch of internships at Microsoft during my PhD. This particular work on recursive program synthesis was completely emailed Sumit, a fellow student, and I, Zach Kincaid. We'd been reading papers on program synthesis. We had some ideas, and we just wanted to get a gauge for whether our idea was sound or not. So we just emailed Sumit, and a paper came out of that. Yeah.
There's got to be a lesson in that for people. It's like the hustle of just, almost like whoever your dream, kind of contributor would be to some paper, just go for it and show them the work, right?
Yeah, and Sumit was, very, very generous with his ideas and his time. And it's paid off. I mean, some of the ideas that he told me back then are, kind of circled back a decade later and helped with the quantum computing work. So that was kind of nice. Yeah.
It's so funny how, you read, all this on paper, and I told myself this story that you had done the internship at Microsoft working on the Prose team, for instance,
No,
it's not even,
there was no
connected.
Prose team at the time, yeah.
Ah, that's cool. All right. I just have to say too, you also did a stint at Amazon Web Services, known as AWS. Was that just to confuse SEO and, confuse the heck out of all of us? Host at AWS.
It confuses everyone. Like every meeting is, the first minute is first confusion and then jokes, and then the meeting starts.
And now I feel bad. I just fell right into the trap.
It's a fun part, yeah.
I want to ask too, before diving into the paper, what's it like, running an academic lab? Your group is doing some really exciting work. How does that kind of, what is that like sort of compared to your industry work and your former academic career?
Yeah, I think one of the most exciting things about having an academic lab is exploring many ideas in parallel with students and seeing how different students attack these problems from very different angles. And then you start with a seed idea for the student, and the student takes it in one direction, but then the student takes you on a journey that you did not expect. So that's kind of the exciting part. And most of the time we're working with PhD students, so it's at least in the United States, it's a long period of time. It's like 5 to 6 years usually. So watching them grow into independent researchers is always just incredible.
That's wonderful. And what about like setting the sort of direction of a lab? Is that sort of all in your hands? Do you have to sort of coordinate with other folks at the university? I always wonder how that happens.
Yeah, in principle, it is completely in your hands. I think the challenges are ultimately funding related challenges. So that's one, whether you have sufficient funds, whether the funds are tied to specific projects. In the United States, again, like the National Science Foundation grants are usually very flexible. So you can work in, a general area as opposed to targeting a specific problem and having deliverables and so on. So that is, it's a nice, in terms of doing basic science. Yeah, and of course, when you're an assistant professor, you have the tenure clock ticking over your head, so you have to pick your problems wisely. So I guess that's another point of pressure. Yeah.
That's so interesting. Yeah. Don't mess it up. No, but they also want notable research too, because that gives
That's right.
them...
Yeah. So it's kind of like this push and pull, where like you want to have something that is publishable with a high probability within a small amount of time, because ultimately you're going to be evaluated. But at the same time, you don't want it to be silly.
Yes, 100%.
So you're playing that time crunch game. Yeah.
Yep. And all of that doesn't take into account like submitting the paper to like all the conferences and revisions and all that stuff, the review, private review. I'm new to this world, so it's always fascinating to me to kind of learn about academia and someone who's so successfully navigated it, especially in our field. So I like learning those behind the scenes. Thanks for indulging me on that.
Yeah. Anyways.
All right, Recursive Program Synthesis, this amazing paper. Number one, everyone should just go read it. I think it's super cool. Among other papers that you've done are also awesome. I swear, I very rarely see Google Scholar, lists of like so many program synthesis papers. So it's pretty, you really are a superstar in this field. But this paper in particular, I think you gave us a little bit of background on how it was, but how did you and your co-author kind of come up with that original idea that made you reach out to Sumit?
Yeah. So as I said, I was, doing my PhD on program verification, right? And automated program verification. So how can you construct a proof automatically? And specifically, one of my early projects in my PhD was on proving correctness of programs with procedures and therefore recursion. And when you're proving a recursive program, it's kind of a very interesting proof technique. Like, for example, let's say you want to prove that this piece of code reverses a linked list correctly, for example. And the proof relies on induction, which is, a standard mathematical technique for proving things. But it's, even though it's a standard technique, it's always like profound and mind bending when you do a proof like that, because, you're proving something about this function. But then when you get to the procedure call, you have to assume that whatever you're trying to prove is indeed correct and go with it. So there's this, assumption there. So I did work in that space, and it was a lot of fun constructing these proofs automatically. And then when we started looking at program synthesis, we set up like a reading group and just to explore the papers that were coming out at the time. And most of the papers were generating straight line code. So think of like bit twiddling programs, like a sequence of, a low-level assembly-like instructions. There was a project called Sketch from Armando at the time, I guess, Berkeley and then MIT. And that was also doing mostly loop-free programs, or if they had loops, they would run a finite number of times. So it's effectively a loop-free program. So we're like, okay, can we extend these ideas to recursion? So it was just a kind of an aesthetic goal, as opposed to, we want to generate something gigantic or synthesize, useful programs. It was mostly like, is this even possible, right? So that's when we started thinking about it, and we were trying to use the similar ideas, like with proofs. You kind of take the property that you're trying to prove and you assume it on the procedure call. And here you have a specification, you have a goal, like I want to synthesize a linked list, and then you're writing the program, you're constructing the program, and when you want to call that function, well, you don't have it because you're writing it, so you just assume that it behaves as you want it to behave, and you keep going, so that there's the recursion there, and then ultimately you come up with that program. So we had that whole idea worked out. This is with Zachary Kincaid, who's now a professor at Princeton, and at the time he was a fellow graduate school student who was also working on static analysis and verification as well. And that was the point when we, if I recall correctly, contacted Sumit. I was like, here's what we're doing. Is this, what do you think? And he's like, yeah, that's great. I've been thinking about similar stuff. And I think at the time we were trying to do everything with SAT and SMT solvers, symbolically, okay. That is. But then he kind of, his view was that, why don't you just start with something simple? Why don't you just enumerate programs? And we're like, yeah, I guess that's easy. And it's easier to implement too. So, we at the time, Zach put together a prototype, OCaml. He was, a big fan of OCaml, so he wrote it in OCaml, and it worked pretty well. To our surprise, that it worked. And
that's always a good moment.
Yeah, and that's and then the rest is history.
OCaml just you started out as like Objective Camel, came out of is it INRIA in France, the lab? That's right. There?
Yeah.
Is that right?
Yeah.
Okay.
Yeah.
Why was he a fan? It's funny. This is kind of in the details, but it came up.
You should talk to Zach maybe. Yeah, but he's a purist. Yeah, so he likes functional programming, and yeah.
Okay.
Yeah.
Well, bigger picture to this recursion idea. So
yeah,
best I can tell, early program synthesis didn't really deal with recursion. Sort of the most classical version. Why are recursive programs hard to deal with?
I guess, it's not true that early program synthesis did not deal. It's early program synthesis in the 2000s did not deal with recursion. But then, So the work that we were building off of did not deal with recursion. But then there was all this work in the sister community of, I guess, I don't know what to call it at this point, but it's the logic programming and AI, classical AI type. So the inductive logic programming community, inherently they were building logic programs, and logic programs are by definition, you have these recursive relationships that you're building, the parent of a person is the parent, the grandparent is, et cetera, et cetera.
That's right.
So,
yep.
So there they were doing things like that and generating recursive programs. We were completely unaware of that whole line of work when we wrote our paper. And it's funny, I recall one of the reviews, even though it was a positive review, they say, it's a funny sentence that I still remember. It said, "This paper sins in that it completely disregards European work." But, since then, I've read those papers and talked to the people, and know them. Yeah. We were doing something that they couldn't do, but we definitely were not aware of that work.
That happens. Andrew Cropper, who created Popper, was a big ILP contributor. Was on the podcast previously, so everyone should go check that episode out. But we're huge fans of inductive logic programming at India, so. That's awesome that you kind of, this is the thing with ideas, they kind of pop up in different places, simultaneously. And that's why discoveries are rarely one person made it. It's sort of like a whole series of things, sometimes unbeknownst to each other. Okay, so the big sort of star of the show, or at least the cool name of the thing, is this Escher, right?
Yeah,
It's an inductive synthesis algorithm, learns this sort of recursive procedure, pretty cool, like input-output examples given that could come from, say, like a user or even like a non-technical user sort of vision of this, like, I guess, like programming by example kind of stuff. Was that kind of the original vision? And also, why the name Escher too? I'm just curious.
Yeah, I mean, I guess, if you look at Escher's famous drawings, they're all recursive, hand drawing itself and all that. So that was kind of our motivation. Yeah. Yeah, I mean, I think, usually with at least program synthesis, traditionally, you have different ways of describing your intent as a user. Like, what do you want to construct? I mean, these days, of course, you can use natural language. At the time, natural language was effectively not an option. So you could either write a full specification, a logical specification of what you want to do. Typically, that's not a great idea, simply because the logical specification ends up looking much like the code that you're going to write. At least in my opinion. You can maybe write high-level properties that you want to abide by, but not the concrete exact thing that you want to construct. And then examples is the other option. So that's what we went with. I guess you asked about the challenge of synthesizing such programs, recursive programs in particular. I think that the challenge is twofold. One of them is that you want the program to terminate. So you are always at a risk of generating something that will recurse forever. So you have to ensure that your search is always producing things that are decreasing for some definition of decreasing. In that paper, we simply used a fixed set of measures for decreasing. For example, if you're manipulating a list, every time you make the recursive call, the list has to shrink in size. Okay. So that's one. You could, of course, go and do crazier stuff. Just generating a proof of termination is also a program synthesis problem, because you have to generate a predicate that says a quantity is decreasing, and what is that quantity could vary vastly between different programs depending on what is decreasing. But for the most part, things are very stylized, and if you're recursing over a list, chances are you're always recursing on a smaller chunk, almost invariably, right? Unless you're doing something very wild where the list grows and shrinks and grows and shrinks and like non-monotonically, but almost always, it's shrinking. So by just fixing that constraint, can take you very far. It can synthesize a lot of programs. And then the other challenge is the fact that as I said before, like when you make the recursive call, you kind of assume the same behavior as the function that you're generating. But here, the behavior is examples. So when you're making the recursive call, you're maybe making it on inputs that are not as part of your examples. So what is the assumption that you make? I don't know. So one of the things that we came up with is the idea of saturation, where you can go and ask the user for more information just to make the recursive call work. So it was an interactive process.
You were foreshadowing the sort of main interaction with LLMs and transformers.
That's right. Yeah. I mean, I ironically, we were doing this at the University of Toronto in, I don't know, circa 2011 or 2012. And then, just a few yards away, Jeff Hinton's lab was building the neural networks that, we know today. So, of course, at the time, they were focused too much on vision. So, there was effectively no connection between our worlds. But, we would hear about their results and.
What a cool time just to be alive, by the way. I mean, just that happened while you're at school, and to see the results of it, and your work is super cool, too. So, I don't know. Yeah, okay, so... That sort of breaks down almost like the problem to be solved. One cool thing that jumped out that feels related to other interviews I've done for the podcast is this sort of components, sort of aspect of Escher. So you build kind of, sequentially larger programs from small reusable building blocks, right? So they look to me like little helper functions. So there's a tail function or a is empty function, and you feed in a list to see if, remove the first item or check if it's empty or whatever. I think that's really cool because it's sort of it reminds me of some ILP stuff too. I can see the connection right there. What do you see as the benefits of components, and where did that sort of aha moment come from in using that?
Yeah, I mean, I guess if you just want to do the search completely blindly, you could just literally enumerate programs without any questions asked, without thinking about it. And then once you find one that matches your examples, you're good to go. But as we were generating programs, we realized that a lot of the pieces of the full program, we were stumbling upon them, right? So why don't we just keep them there and then stitch them together later once we find all the pieces before actually stumbling upon the full thing right off the bat? So if you're just synthesizing, for example, an if statement with two branches, you may find one branch that solves some of your examples, but another branch that that solves a different set of examples. And then you can keep those together and figure out how to use them properly. So now your problem becomes synthesizing the conditional that stitches together those two pieces of code. And on and on. So this is where we came up with this idea of a goal graph that essentially tracks which sub-goals or which examples you can solve with which sets of programs, and then how can you stitch them together.
Oh, that's cool. Okay, so it wasn't like a initial specification or something. It was
it's a data structure that is internally maintained by the algorithm. These days, perhaps if you're using agents, in some sense, they try to do things like that. It's like, oh, look, I have a file over there. Oh, there's a script I could use, and you cobble together a bunch of things that are available.
Yep. Markdown files, maintaining state everywhere.
Yeah. So that's where it came from.
That's really cool. So was the goal graph specifically and the components, like, it sounds like they were kind of iteratively discovered. So you were running, you do the base thing and you're like, oh, we're just repeating things over and over. Let's make use of that. How do we keep track of that? Okay, we need some sort of structure. This is the goal graph. Was it sort of iterative like that?
Yeah, it was completely iterative. And I think when we first implemented the goal graph and it, improved things, we thought of it as a hack, right? But when we wrote the paper, we're like, well, that's actually kind of cool. There's
this is like the harness conversation.
Yeah, oftentimes that's what I see also, like you asked about, like, what is it like working in an academic lab is, oftentimes students, discover interesting things, but for them, it was just like a rite of passage. Like I was getting there and I had to do this along the way. I'm like, this is actually very cool. Like you should highlight it, So just, looking at your backwards at what you've done and cleaning that up into a nice story is a skill that, we try to teach students,
Yeah, you're as their professor now and advising folks, you could probably you can have that higher level view and be reward them more short term of like, this is cool, you should pay attention to this, because they won't see it. Like everything's new and everything's you're in the weeds of like what the paper you're working on,
right,
thesis.
Right. Yeah.
Another one that jumped out at me was sort of something we care a lot about at India, which is search guidance. Program synthesis, the classic problem is search. Like, even if you can define the right program, the correct program, then how do you find the darn thing, right? So like, combinatorial explosion of possibilities, so search guidance was like a big part of Escher, right? So can you explain to me just like kind of nuts and bolts of what you came up with for Escher?
That's exactly right. So when you're generating programs, you're generating sequences of instructions, and you're like, oh, this sequence can solve these examples, and that sequence can solve that other example. And if I put these two sequences together, now I can solve everything. And now the question becomes, is inverted, which is, well, how can I synthesize this conditional that splits the program into two pieces, one that solves one set of examples, the other, and does there exist such a conditional? So that's why we call it the backward search. So now you're trying to retrospectively fix your work. So forward generates these snippets, and then backwards is stitching them together.
That's super cool. Did you feel like happy with that discovery? Did it work well? The results were good?
Yeah, the results that improved the search significantly compared to, say, completely blind search. So it was essential to the success of that approach.
Yeah. I thought you did a great job. There's this whole section for implementation and evaluation, which is just so, it's like everything's wrapped up nicely with a bow, You already talked about the OCaml prototype.
Yeah.
the benchmark side, there's the usual suspects of, integer, list, tree domains. Yeah. But as you mentioned earlier, from Armando Solar Lazama from MIT, Sketch. You also did a comparison against the sort of Sketch tool. Well, why did you choose to do that? And what's cool about Sketch, I guess?
Yeah, so it wasn't, a fully fair comparison, because Sketch was targeting, at least at the time, it was targeting a different domain, kind of more low-level code, more bit twiddling. But there was nothing else out there that we could compare against in terms of open source tools that could even do something remotely similar. So at the time, the Sketch was the only thing. So we found a way to, hack our problem into Sketch and see how Sketch would do it. It didn't do very well, but it's not it's not a problem with Sketch itself. It's a problem with the problem and Sketch together. Yeah.
Mm-hmm. How about the other benchmarks? What were the results on integer, list, tree domains, those ones?
Yeah, we were surprised that we were able to find lots of programs really, really fast. And if you think about it, most recursive programs, at least like this, functional programming 101 style of recursing over a list, reversing it, etc. They're relatively short, right? Like there's a base case and there's a recursive step. Maybe in some instances you need mutual recursion or something like that. But they're fairly small snippets of code. So essentially that was what was the benchmark suite is those programs. Again, at the time there was no fixed. It was it was the Wild West, right? So there were no tools. There was no set benchmark suite that you have to check all those boxes before your paper can make it or anything like that. So we were just making stuff up as we went. Yeah. So that was It's always nice to work in a new area like that. It can feel disorienting, but it is also liberating at the same time.
Yeah, and it's not just benchmarks as marketing tools like they are now.
That's right.
It's actually serving a real purpose that you had a utility you needed solved for. What about as compared to you mentioned SAT solvers, SMT based synthesis? How about compared to those methods? How did Escher fare?
So that was the Sketch comparison, because Sketch, the way it worked, at least again at the times, it's been a very long time, and a lot of things have happened. But its innovation was an encoding down to SAT solvers. So it would, at least the first iteration of Sketch would, you had a language with holes where you just can literally say, I don't know what goes in here, and it would find the constants for you. So at the time it was only constants, but then you can hijack constants to make it full-blown trees. Meaning ASTs. So essentially, that was the comparison to SAT solvers. Yeah.
That's awesome. All right, I need to brush up on Sketch, obviously. I have to say, I spoke with one of your past students, Calvin Smith, earlier today, and he was mentioning that this paper, it has a lot of citations, but it doesn't have nearly as many as it deserves for the sort of where these ideas were at the time, and maybe the impact that the paper had. What do you see as the kind of relevance of this paper toward work that followed it, and any parallels that sort of popped up that seemed very valuable that you were on the same chase for?
Yeah, I think after that paper, a number of teams wrote papers kind of refining these ideas in many different ways. So including both using types to prune the search in a more disciplined way. Our approach kind of did not take types into account at all. So we were just, enumerating programs. A number of papers gave it a more disciplined type theoretic view. The goal graph idea showed up in different guises in other program synthesis papers. So those I guess were the contributions. The fact, one, that you can actually do recursion and it can take you very far. So some people kind of took it and made it more disciplined and from a functional programming perspective, type theory perspective. And then those underlying data structures that I've seen in other works as well.
Thank you for going back in time and kind of looking at a sort of paper that's been a few years for you, but I do think it's very important. And for the topic of the show, just super relevant and really cool work. So I really appreciate that. Let's bring it
thanks.
A little more into the present. You took program synthesis quite far into the future, and now you're into the quantum world, which is just wild to me. What role do you see, symbolic AI, including program synthesis, playing in the sort of quantum world. Like how did you get there too? And just what role does it play?
Yeah, so I can, I guess, tell you my history and how we're applying program synthesis in that space. So I guess after I got tenure in 2020, 2021, and it was also COVID, so we're in lockdown, and so I was both kind of stuck at home and thinking about what am I going to do next in my career now that I have all that time and freedom, and I was just stuck at home reading Einstein's biography, and this is all the part about quantum. yeah. That's what you do in a pandemic, right? And there was the part about quantum mechanics, and it was kind of exciting. So I was like, well, there's all this stuff on quantum computing. I wonder what can I do in that space? Maybe there's something. So I started looking around. Around that time, we hired a new professor. His name is Sumit. He's a computer architect, but focused on quantum computers. So he's very low level, understands the hardware and the nuances there. And I started talking to him, still on video because we couldn't meet in person. And one of the things that I realized that the space is there's lots of research and lots of people, very, very smart people working in the field. So it's kind of a very exciting field, especially from a physics perspective. There's tons of companies. There's, multiple Nobel Prize winners are running, big companies, etc. And they're applying vastly different technologies at trying to build quantum computers. So, when we think of traditional computers, really just the transistors and, put them together in different shapes and sizes, and, you have chips. But there, it's like you're talking about vastly different technologies that you can't transfer skills from one to the other, and people are betting on different technologies, from like photonic computers to neutral atom computers to superconducting computers. And then they're, what's interesting is that they're all moving in lockstep. They're moving slowly ahead. They're not doing anything commercially useful yet, but they're all moving in lockstep. So it's a very fragmented space. And things are moving fast in the sense that, the architectures are constantly changing. The protocols that you're running are constantly changing. So if you're building any kind of software on top, that software has to adapt on the fly. A physicist might have an idea and suddenly your instruction set changes completely.
Yikes.
So the idea that I had was, can we automatically generate compilers for such computers? Because ultimately, even if these computers are not doing anything interesting, having a compiler allows you to ask questions like, for this application, how many resources do I need? How many qubits or quantum bits do I need? How long will this computation take? And without a compiler, you can't answer these questions. So even not about even running stuff on the computer. So we started looking at the question of synthesizing compilers for this, and we've been down this rabbit hole for quite a while. Now with pretty fun results. So we have kind of a.
Let's hear the results. By the way, I got to know.
Yeah. I mean, if you think of a compiler for quantum computers, it looks very much like a traditional compiler. Mostly it's lower level though, because the kind of computations that we're writing still are low level, in the same way that compilers in the 70s are not like compilers are now. So we're mostly dealing with kind of assembly level instructions and mapping them onto a device. So that's kind of roughly what we're talking about here when we talk about a compiler. So we figured out how to synthesize optimizers. So an optimizer is, again, as you expect with a traditional compiler, where you take a program and you want to shrink it as much as possible so that it runs more efficiently. And when you have machines that are worth millions and millions of dollars, you want to be very careful before you call them. So your computation better be small. And they're also very noisy at this point in time and very error prone. So if your computation is too long, you're just going to get complete garbage at the very end. So you have to shrink it as much as possible. And as I said, the instruction sets are changing rapidly. So we said, okay, give me an instruction set. I will give you an optimizer for that instruction set. So that's that was our work on optimization, and we managed to push it hard in the sense our automatically generated optimizers can outperform like handcrafted ones that people have been working on for a long time. So that was kind of fun.
What a cool discovery.
Yeah, it was a lot of fun, and then and then things diverge from traditional compilers. Like if you think of traditional compilers, you always want to transform your code into another piece of another language while maintaining correctness, meaning it has to be the same, right? But with quantum computing, because everything is ultimately real valued or complex valued, you can never get things absolutely right. So you have more leeway as an optimizer to approximate. Which is kind of nice. So I can take a piece of the program and be like, well, I'll give you a slightly different piece, but it's much smaller, and plug it in. So the program synthesis problem becomes more, I guess, approximate program synthesis as opposed to
Less constrained or something.
Yeah. So that was fun in that. And then going lower level to the actual device constraints. The devices are, as I said, like vastly different from each other. So some devices, like neutral atom devices, you can literally move your bits around in space. They're literally atoms, and so you can bring
like
two atoms.
sci-fi.
Yeah. So you can literally, they use lasers and they bring the atoms together, and you can entangle them, and then you put them back in space. So now those two bits are entangled.
That is just so. What functions, like what use cases are there for these computers? Like, I mean, and I know we don't even know yet where it could go, but like what you just described, what are you calculating? What are you producing? What's it for?
It's a big question in the quantum computing space, but historically, the big excitement in quantum computing arrived in the mid 90s. So from a computer science perspective, it was Shor's algorithm, where you can break public key crypto and by factoring integers efficiently. And this is a problem that we think on a classical computer you can't do. So you have an exponential speed up, assuming you have a quantum computer. So that was kind of there's something there at that point. So people started paying attention, and then from a scientific perspective, simulating molecular dynamics and chemistry. So that's the other application where we also know that you can get exponential speed up. So those are the two major classes of applications that people are interested in. There's also interest in algebra and linear algebra and machine learning. Again, there are classes of algorithms where we know how to get exponential speed ups. But there, the story is more murky because of the constraints that you assume on the inputs. It's not like you can throw any matrix at it. It has to be sparse and so on. So whether these constraints are realistic or not is still kind of open. So those are the big applications. And the view is that if you can simulate, for example, chemistry really efficiently, then you can enable drug discovery and material discovery and so on. So those are the applications of those computers.
And a lot of that is future facing stuff. Wait, one thing that popped out to me too, and those are a series of papers that you were kind of riffing through there. Like there was one on like PLDI 2023.
That's right.
Synthesizing quantum circuit optimizers, and then the other one you were mentioning was generating compilers for qubit mapping and routing. I'll link them all in the show notes. Go check them out.
Yeah. Oh, I was going to say, yeah. So the PLDI paper was on optimizers, and then the Popple paper on generating mapping and routing. This kind of looks at the low-level devices. So it takes into account whether a device can move atoms around or it cannot. Some devices cannot. The qubits are fixed in place. So how do you have them talk to each other? You have to start swapping them around and so on. It's kind of like a grid. So you're solving different puzzles, and and people kept writing papers and still do on how do you do a compiler for this kind of device versus that kind of device and so on. So we took the program synthesis approach and said, well, can we synthesize once and for all compilers for all of them? And so we looked at all those problems and we figured out an abstraction. So essentially the way it works is like a designer, like a quantum computer designer, like think of a physicist, for instance, who figured out how to build a chip. They write down the specification of the device, and out comes a compiler from that device.
That's awesome.
Yeah. And last summer, my student Amanda Zhu was at Google, and they were, working on their next iteration architecture, and they used our compiler generator to generate a compiler and study it. So that was that was a nice validation of our approach to, so it's it's not overfitted to the benchmarks, So that was
this is like the only one of the only places that quantum computers actually like really exist, right? At Google and maybe a handful of other places.
Yeah, Google is a pioneer in this space. Yeah,
Tell me about this too. I don't quite understand like this logical qubit and physical qubit. There's some sort of that's the mapping in the name of the paper, the sort of compiler one. What is that? I'm so curious about like what that even means.
So typically, if you think of your program as the program that you've written on a piece of paper or you've written in your IDE, that's your logical variables, and then your physical variables are what sits on the device. So think of like in the traditional compilers, you have the variables in your program, and then the registers and memory locations. So those are the physical places where your program will actually live when it gets to execute. And it's the same problem here. You have the logical bits in your actual circuit or program, and then the bits or the qubits on the actual physical device. And you have to map one to the other. And then you have another layer of complexity, which is the fact that these computers are incredibly noisy or susceptible to noise. And your laptop and my laptop are also susceptible to noise, but the probabilities are so low that we don't think about it at all. Of course, on networking we do, there's packet loss and stuff like that. But in general, like on a laptop, when you run a program and it doesn't work, you don't think, oh, a bit's probably flipped. No,
it's a bug.
It's probably more likely it's a bug, right? But quantum computers, you're talking about error rates like 1 in 1,000 right now, or meaning 1 in 1,000 instructions will fail. So pretty much anything you're trying to do is incredibly noisy. And to mitigate noise, you have to do error correction. And error correction on a quantum computer works in the same way as with a traditional computer. You just replicate the bit. So instead of writing your name once, you write it 10 times. And so if one of them gets mangled, then you look at the others and you're like, okay. So you do something similar. It's much more complicated, but ultimately that's what it is. You pack a bunch of physical qubits and you call them, this is my logical qubit. So here the word logical becomes different. It's kind of like a more programmer facing, like from a view of the programmer, this is what a bit is, but under the hood, it's really many bits pretending to be that one. Yeah.
That is cool stuff. So where do you see all this going? Is your lab going to continue pursuing, quantum, getting validation? It's being used at Google.
Yeah.
And just your own personal kind of passion toward it. Is this like the thread you want to keep pulling?
Yeah, I mean, I think a large focus of my lab will continue to be in this space. I think there are so many open problems in this space, and we keep stumbling upon others. And it's also a fast-moving space simultaneously. So there's developments every week, every day. It's in the same way that AI is also fast-moving, where you wake up and you check archive, and it's like, what happened overnight? So it's very similar, but of course it's still more early stage. So I feel like coming from a programming languages, formal methods background, there's a lot to give. And then as we saw like with those papers, so there's more opportunities elsewhere as well.
What do you have to say about the sort of challenges with all this agent stuff going on? Agent fleets and or like correctness of agents. It seems like a big hot mess. I mean, you've got the open clause and the Hermes agents, and it feels like very early days. Although we're starting to see some pretty cool outputs from these things and people finding new use cases. But where do you see your expertise kind of playing a role in that world?
I mean, I come from the formal methods background, so I think of things in terms of properties and, what does this piece of code satisfy and so on. And, I mean, if you think about it, like right now we've been writing and building agents in a very ad hoc fashion. It's like, just give it a bunch of tools and let's see what it does with them.
Yep.
And now people are like, we'll need some security boundaries. But the questions are very, very challenging, right? Because, just think of the problem of prompt injection, right? It's ultimately it's equivalent to the problem of you looking at an email and detecting whether it's a phishing email or not, right? I mean, you probably get it right most of the time, right? But there's always a probability of failure. I mean, maybe you're tired, whatever, you're not paying attention, you didn't check the address, etc.
Oh, they're getting more clever. Yeah.
Yeah, yeah.
We had one yesterday. It was one of our newest teammates, new researcher on the team, got a fake text from one of our co-founders, not from them, that like masquerading as them, and even like took it as far as a couple exchanges of like, he was like, to verify it's you, can you tell me what paper we just submitted, blah, blah, blah. And it was like the wrong answer. And so it was obviously, but there was like some thought going on behind this like attack, essentially, I don't know what they were going to do with it. Maybe get access to our Google account or something, it's a bit of an arms race with AI in this sort of security, challenge. But okay, back to formal methods within that world, though.
All I'm saying is that it's a very challenging problem because there's no clear boundary that you can draw. Like there's no piece of code that you can plug in that will detect phishing emails 100% of the time, right? And it's the same thing with agents. The more access you give them, they're going to see more information, and they're going to be fooled by some of that information, some small percentage of the time, no matter how good the agent is. And I feel we have to live with that one way or another. There's not going to be especially as we give agents more and more power. There's of course very interesting mitigations to prompt injection and stuff like that. But ultimately they rely on stripping power off of agents. For instance, there is like this popular paper that came out of Google and others, and this Simon Willison, who runs a very popular blog, on essentially separating. I forgot what the terminology that they use, but essentially you have the agent plan its actions ahead of time. And by planning its actions ahead of time, that implies that if it sees something weird along the way, it's not going to backtrack and start, deleting your files because its actions are already planned ahead of time. Yeah, so that's great, and it works beautifully. It can protect against many forms of prompt injection with provable guarantees, but at the same time, now your agent is pretty static, so it can't dynamically react to the environment. Like if you tell it to open a file and it only thinks that, it was the wrong location, then it's stuck. It can't now backtrack and be like, oh, no, I'm going to look for it somewhere else. So that's kind of like that. Those are the challenges that I see. There's also, of course, a lot of information flow challenges, meaning like if it reads an email, can it send it to someone else now? The permissions. And the problem is that, these things are hard to track because once you enter an LLM, what comes out is you can't say that what entered it is the same thing as this piece of information, because it could, wrap it in a different way, describe it in a different way. So once something enters an LLM, it's essentially a black hole, and you can't track it outwards unless, of course, it's syntactically the same. But otherwise, it's you don't know what happened. So reasoning about all these problems is fascinating. I'm not sure what the right answer is, but it's something worth exploring. But again, it's a very fast moving field, right? The way we're building agents today is probably going to be vastly different from 9 months from now, let's say.
Absolutely. It's like the one thing you can count on, probably. It's just it will be different, and we'll have learned a bunch of stuff, and we'll probably be surprised. I guess one thing that surprises me about that too is how practical, like the use cases you were thinking of there, like the email access and whatever. Normally folks in this world are about program verification of the LLM, code gen output or something. It's a little more lower level, and there's a place for symbolic AI to play there for sure. But I just really like how actionable the stuff that you're talking about was. This is a former Zapier, first product designer there and co-founder of our company. So I love workflows and automation and all that stuff. But I just like hearing how you're applying it to very valuable, meaningful stuff to every worker, probably. More so than the qubits and the logical qubits and the physical qubits, maybe.
Right.
You got a foot in every sector.
You got to hedge your bets, right?
Yeah, I have to say, I do see kind of an overarching theme to your work, which is kind of don't keep over and over synthesizing. Don't keep coming up with the algorithm, the compiler, the optimizer. Don't hand engineer those, and don't do them each time. Synthesize them. Use synthesis to create a sort of, generalizable single solution that covers all those needs. Does that seem accurate? Because it's a really elegant.
Yeah, that's the theme of my
thesis.
research, and you put it better than I could have.
Ah.
Yeah.
No, it's there. It's so clear. I'm hearing you say it each time and just in different ways and very different applications. But it's like, you used to have to do it this way and hand code each one. And that's ridiculous. Like for quantum circuits or, so it's fascinating. It's like a very elegant problem that you've been solving in different ways, like your whole career, You could endlessly do that. It's a pretty cool thing. You should write a book about it or something. I think it'd be pretty cool. Actually, you did write a book. You have a book. It's kind of like neurosymbolic, right? It's like neural network verification.
Yeah.
Is that right?
Yeah, that's right. Yeah. So this came out of both of a line of work that we were doing here in terms of what does it mean to even verify that a neural network is behaving correctly. And at that point, it was just a neural network in isolation. It's not an agent running in a loop. So the book essentially explores how you can apply ideas from program verification to analyzing neural networks. So that came out again during the pandemic. It was a very productive time. I was teaching a class when the pandemic hit, and the class went online. But it was a class exploring this idea, and I used the class as a way to force myself to write something about it and teach it to myself as well. So a book came out of it. Yeah.
That's awesome. What an actionable way to process information. I'm sure everyone, like the students, appreciated it too. It's funny how relevant that remains.
Yeah, I get a lot of emails about liking the book and using it in courses and stuff like that. So it's always nice to receive those. Yeah.
We got to mention it's free online, by the way. You can grab the PDF from Aws's website. So I'll link that in the show notes too. Thank you for making it available to everyone. Wrapping up, what do you see? We've covered so many cool use cases of program synthesis and symbolic AI. What haven't we mentioned that you'd point, researchers toward as like really cool, ideas to explore in this space?
Yeah, I think now it's kind of we're reaching a point where all ideas from both symbolic world and the neural world are coalescing in some sense, and it's become hard to tell whether something is symbolic or neural or what. The work that agents are doing is essentially they're both synthesizing programs in the sense you can ask an agent to generate code, and that's a form of program synthesis. But at the same time, they're also the way they operate is somewhat symbolic. If you hide the LLM away, it's really constructing a plan, which is a bunch of tool calls and stuff like that. And those tools can generate programs and so on. So we're back to recursive program synthesis in some sense. So yeah, I guess there's lots of questions about how we're going to be doing software development in the future. I've been of course producing a lot of code with these agents, and the way I've almost never look at the code, and I kind of got to a point where I can work or I've co-evolved with these agents, if you will, and so I understand their weaknesses and their strengths. They fool me sometimes, but for the most part, I can steer them to very, very interesting places and build very complex pieces of code without looking at any of the outputs, by just having them test properly, validate properly, and so on. So that's kind of an exciting place to be, and in such a place, problems from verification come in. So not only can you test, you can have the agent also prove itself, and so that's very exciting. There's lots of research these days in this space, but of course it's not yet the way we build software. So one can ask, how long will it be until we get there? I don't know, but I think lots of research will have to be done in that space, and tooling has to be built. Right now we have very strong tooling like Lean, but Lean kind of lives in isolation from pretty much all other programming languages and environments. So how can we connect the two? Maybe there's something other than Lean. Maybe Lean gets incorporated in some way as a library into other. I don't know. I'm just kind of shooting from the hip. But the world is changing very fast, so I don't have anything wise to say. Yeah, I'm just in it for the ride.
Read your papers. There's plenty of wisdom in there, but I don't know. And if those ideas excite people, are you looking for new students for your group? Is that something people should reach out about?
Yeah, I'm always looking for new students. And as I said, as we talked about, we're working both in quantum computing as well as agent construction and combinations of those. So that's pretty exciting. For example, we talked about generating compilers automatically, but you can now imagine generating new computer architectures and compilers for them and evaluating whether these architectures are good or not and iterating. So we have, we're trying to build that full loop as well. That'll be fun. Yeah.
You're going to take over quantum right there. You're going to have the whole stack. It's amazing. I can't wait to see what you come up with. And I would just say you've got some amazing talks and presentations on about like your personal background with research and also just about specific topics on YouTube. So I'll link a couple of those in the show notes. But folks you can just search for your name and you'll come up, and it'll beat out over that terrible other AWS spelling thing, which you're always competing with. No, I'm just kidding. But I really appreciate it, Aws. You're awesome. I kind of feel like you should have an open invite to come on anytime. Maybe if you have any of your students who have a cool paper come out, shout us out. Like if you want us to cover it, happy to feature you all because you're doing great work. We could chat about your past papers too. But thank you so much for your time and your work.
Yeah, thank you. Yeah, thanks for having me. It was exciting.
Awesome. All right, everybody. Thank you so much for watching, and stay tuned for more cool paper deep dives like this on Abstract Synthesis.